Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 16, Organic Chemistry 1. Today we'll start chapter 5, the study of chemical reactions. The most interesting and useful aspect of organic chemistry is the study of chemical reactions. When we go to the lab and start performing experiment, several questions come to our mind. Why is heat, light, microwave, ultrasonic, or even cooling needed for the reaction to go? Why do we get a mixture of products? Is there any way to modify the reaction to get just one pure product? Are the observed products formed because they are the most stable products possible? Or are they favored because they are formed faster than any other products? Jump to our mind, and the answer to these questions involve three aspects of the reaction. First, thermodynamics. Thermodynamics is the study of energy change that accompany chemical and physical transformation. It allows us to compare the stability of reactants and products and predict which compounds are favored by the equilibrium. Second, kinetics. Kinetics is a study of reaction rates, determining which products are formed fastest. Kinetics also helps to predict how the rate will change if we change the reaction condition. And finally, we come up with the mechanism. The mechanism is complete step-by-step descriptions of exactly what bond break and which bonds form, and in what order to give the observed products. In thermodynamics, a measure free energy. The free energy is a potential energy of the reaction, can be used to predict the properties of a chemical reaction. In the late 1800s, Gibbs showed that free energy G of a system can be defined as G equal H minus Ts, where H is the heat energy of a system. So we will consider the reaction as a system. T is the temperature in Kelvin. S, another function called entropy. Heat energy is a measure of energy in a chemical bond. Tightly bonded molecules have higher heat energy. كل ما كانت الرابطة قوية كل ما كانت الانرجي عالية. Entropy is a measure of disorder of a system. Molecules distributed randomly have high entropy, large S, while ordered molecules have low entropy, small s. And we end up by that delta G equal G of products minus G of reactants equal H of products minus H of reactants minus T S of products minus S of reactant, which means that delta H minus T delta S. We are recalling that from General Chemistry 1. The standard Gibbs free energy change, we give standard by naught equal delta H naught minus T delta S naught. Notes mean that the reaction involving reacts and products and are in their standard state. So pure substance in their most stable states at 25 degree and 1 atmosphere pressure. That means note, at pure state, temperature 25 degrees Celsius, pressure 1 atmosphere. Let's talk about enthalpy. H is used to quantify the heat flow into or out the system in a process that occurs at constant pressure. Delta H of reaction equal to delta H of formation of products minus delta H of formation of reactants. Or you can write it differently. You can say is delta H naught bond broken minus H naught bond formed. Remember, when you form a bond, you release energy, give out energy. When you break a bond, you need energy. And when you need energy, this will be positive value. When you when you form a bond, you release, and this will be a negative value. Delta H equal heat given off or absorbed during a reaction at constant pressure. Let's see if we change water from solid state to water in a liquid state. Okay? Of course, the energy of water in a solid state will be lower than water in liquid state. So this absorb energy from the surrounding, and we call this endothermic reaction. Call it endothermic. The content of energy in products will be higher than the one in reactant. Delta H is always positive. In case of burning methane in oxygen, okay, giving out carbon dioxide and water, this gives out energy, so this is exothermic reaction, okay, and the H of the product will be lower than in the starting, so we get energy out to the surrounding. Also, you recall that from general chemistry we have what we call it reaction profile. This is the energy level of the starting material. For the reaction to go, we have to give a little bit energy, we call it activation energy, and then we get a product at lower energy level. So we have delta H naught, okay, and this for the exothermic. While if the energy level of the starting is less than the product, okay, the delta H naught will be positive, and we call this is the reaction profile for endothermic reaction. For a bond-breaking reaction, delta H is primarily determined by the amount of energy necessary to break the bond homolytically. That's the scientists agreed upon, and we call this bond dissociation energy. It gives approximate data for what's going on, since not in many reactions the break of the bond, instead of occurring homolytically like this one, each one gets its own electron, X radical plus Y radical. Many of the reaction occur by heterolytic cleavage, giving X plus Y minus. Anyway, the term delta H naught refers to the bond dissociation energy when measured under standard condition. Once again, 1 atmosphere, and the compound in its standard states is either gas or pure liquid or solid. Predict the sign and magnitude of delta H naught for the following reaction. Give your answer in units of kilojoule per mole and identify whether the reaction is expected to be endothermic or exothermic. Given bond dissociation energies, delta H naught for isobutane CH, for CCl bond, for CCl bond of tertiary butyl, and HCl bond. If you apply delta H naught bond broken minus H naught bonds formed, then you write the bond dissociation energy as given. So for bond broken, it's 381 plus 242. That's for these two bonds, minus bond formed, the CCl and HCl, 331 and 431. And the net result will be minus 139 kilojoule per mole. It's negative sign, so it is exothermic reaction. It's exothermic reaction. On the other hand, if you apply delta H of reaction equal delta H of formation of products minus delta HF formation of reactant, remember that delta HF of formation, okay, should be negative value. So we will start the product, okay, so we will sum 331 and 431 will be minus 762 minus 623 equal to minus 139. Okay, so we have just to take care of about the delta H. F minus should be with negative sign, okay. Predict the sign and magnitude of delta H naught for the following reaction. Give your answer once again in kilojoule per mole. Identify whether reaction is endothermic or exothermic. Given bond dissociation energies for C double bond by bond, if you break by bond, 264 kilojoule per mole, HH 436, CH 410. In here, for the reaction, we break this by bond. If you break the by bond to 64 plus HH bond 436 minus, you have formed 2CH, so 2 times 410. Okay, you end up with minus 120 kilojoule per mole. The reaction is exothermic again, exothermic reaction. Okay, And the rule, what the delta H naught is equal to delta H naught bonds broken minus delta H naught bond formed. Entropy. Entropy is simply a measure how much the energy of atoms and molecules become more spread out in a process and can be defined in terms of statistical probabilities of a system and in terms of other thermodynamics quantities. The value delta S system is affected by a number of factors. The first, an increase in entropy because the number of moles of the product are higher than that of reactant. We have here one reactant. Remember the cracking? Thermal cracking of alkane will get it smaller alkane. So we have here methane plus propene. We have here one reactant, but here we have two products. Two products. So the net, you increase that by one more, right? So if you have more moles of products, then you have higher probability of randomness, and that means that delta S is going up. Another, you start with one mole, but in cyclic form, and you end up with it in acyclic structure. A cyclic structure adopts a large number of conformations than acyclic compounds. So again, the randomness here increased. A cyclic compound is being converted into a cyclic compound. Such a process also represents an increase in entropy, okay? Because acyclic compounds have more freedom of motion than cyclic compounds. Calculate delta S naught for the combustion reaction of liquid isooctane. Isooctane liquid, oxygen in its gas phase to give CO2 gas phase, water in the gas phase. Remember here now that you have to count number of moles. So here is 1. Here is 25 by 2. Here is 8. Here is 9. They gave you S naught for CO2, 213.8 joule per mole dot Kelvin. S naught for water, 188.8. For octane, 329.3. And for oxygen, it's 205.2. Delta S naught for reaction equal delta for S naught of product minus delta sum of S naught for the reactant. Remember that you have to count number of moles for each. Here we have product 8 CO2. So 8 S naught for CO2. 9 water. 9 S naught for water. Minus for reactant 1 mole for isooctane plus 25 by 2 S naught for oxygen. So it will be 8 mole of CO2 times 213 plus 9 times 188.8, then that minus the sum of 1 mole of C8H18, which is equal to 229.3 plus 252 times 205.2 and that you end up with value of 515 in a positive value, and that means that you have entropy positive, entry, entropy positive. In summary, delta G is equal to delta H minus T delta S. For the reaction to be spontaneous, delta G must be negative value. Well, if delta S is positive and delta H negative, so this will be negative value, and since delta S is positive, then this value will be also negative. The total will be negative, so this condition will be spontaneous at all temperature. Now, if delta S is positive, if this is positive, but delta H also is positive, for the total to be negative, this value has to be larger than this, the delta H, right? So here is positive, and here is positive. At very high temperature, this value will be higher than this, and the total will be negative. So the reaction will be spontaneous at high temperature, where exothermicity is relatively unimportant, which means that this part will not be important part, but the entropy will be the one we consider. If delta S is negative, this means that since here is negative, so if delta S is negative, this part will be positive, okay? And exothermicity will be very important, and the reaction will be spontaneous, but at low temperature, As delta S negative and delta H positive, so if this is negative and this is negative and this is positive, okay? If this is negative and you have minus, this means that you have a positive. Positive and positive, the total will be positive. Accordingly, the process not spontaneous at any temperature, but the reverse process going the other way around is spontaneous at all temperatures. See you in the coming lecture.